So, welcome to the first video on graph properties, now that you're familiar with the terminologies that we're going to use in this class. Graph properties have different dimensions. We first want to talk about undirected graphs. So, an undirected graph here really matters from the perspective that each edge represents a bidirectional relationship. So it does not matter who connects to whom, it only matters that two edges are connected. Two knots are connected, sorry. The two knots are connected with an edge, and it does not matter in which direction they are connected. So the connection between those two knots is symmetric. It counts the same way from knot A to knot B as the other way around. And we represent such a graph normally by two factors. We list the vector by the label V. We use the set of nodes as an vector, and in E, normally in a matrix, but all of that later in videos, set the edges so you can see which is connected to which knot. And all of that is unordered because it does not matter in which order they are connected. It only matters if two knots are connected or not. And this is how it looks like. Here we have 6 knots and we have 7 edges. So the knot 1 is connected to the knot 5 and 2 with the edges 1, 5 and 1, 2. So the connection goes both ways. It's, as I said, only matter of fact if they are connected, not how. This is quite the abstract thing. It would be comparable to people that talk to each other or phone calls. It does not matter in this case who calls whom. It only matters that the call happens. This is different if we talk about directed graphs. Sometimes they are also called digraph because they are directed. And here it really matters that the knots are connected in a direction. So the edge has a direction, and we will draw this in a second as an arrow to make sure where the edge has its source, where it's starting, and where it ends, so where its target is. And we store them similar with the knots and the edges in a graph here in this curl G. And it looks like this. We have here 2 just to make sure that the difference is clear. On both of them, we have directed graphs, so it really matters that the knot 1 is connected to the knot 2, but the knot 2 is not connected to the knot 1. And the difference between those two graphs is the arrow between the edge 3 and 5. Where the direction really matters, that we switch them from the left to the right graph. And so you might have to zoom in here a little bit, but this is really where the difference is in those two graphs, and they have therefore a completely different meaning if they are directed graphs. If we have undirected graphs and switch this direction of an edge, it does not matter because the direction really does not matter. So also there is no source and target of the edge. Here in the directed graphs, it actually matters. We can also have weighted graphs, quite also an interesting concept which we will encounter more often in economics, because we can assign numeric values, or a weight, this is where the word of a weighted graph is coming from, to each edge. So we reflect the intensity or the significance, how important the relationship between two knots is. And we can, in economics, quite often we use costs, capacity, distance, all of that stuff can be weights. So if you think of a transportation network, we can have the two cities, let's say Berlin and Paris, and we have the connection between them either in a geographic distance or in time to travel. All of those things are possible. If you talk about communication networks, we connect two knots with bandwidth or signal strength to understand how much information can flow between those two knots. And in economic networks, where we will move into later on in input-output modeling, we model trade volumes between two places or two sectors to understand how much is flowing from one sector or one region to another sector or region. We can also calculate or state transaction costs. How costly is it to get from one point to another? All of those things can be quite easily imported in a weighted graph and then done math with and understand that graph and store it and process it. We can also have multi-edged graphs. So this is where a graph which has knots that can have multiple edges between the knots. So what the ones I've shown you so far is quite simple, where we have one knot and another knot and we connect them with a straight line. But we can also have multiple connections between those two knots, and that they actually matters. So if we think of this parallel edges as a concept, how it could happen, you could have two people in academia that work together multiple times, so they are connected multiple times. We can also show with that redundancy in resilient networks, and so how many connections are there? If you think of the connection between Paris and Berlin, how many streets are connecting those two cities, or how many train lines? Can we remove one? Can we not remove one? Do we need them? Especially if the multi-edge graph is weighted and you're like, oh, we have train tracks there, and on one train track 5 trains an hour can go and on the other one 10. That would add up to 15, but because in the context of the network that we're analyzing, it matters that they are two separate train lines, and therefore we cannot just add them up here. This is how it looks then. Here we have the different knots connected between 3 and 2. We have 2 edges, so they are redundant from a perspective of mathematical perspective, but from an economic understanding, they might actually matter. And there's a reason why they are there. Here at 6, you see this loop again. Between 1 and 5, you actually have 3 edges. So even there, a multigraph in its perfect form. An example for those graph properties could be, for example, if you think of interbank lending market. We have 2 banks. These are the knots, and they lend money to each other. And the directed edge shows you in which direction the loan goes. So it goes from bank 1 to bank B. And we weight that whole thing with the size of the loan. So it's 2 million euros. And if you have multiple edges, each of them represents an individual loan. So bank 1 has perhaps 50 loans to bank B, and all of them have different varying interest rates. So all of that has to be incorporated into that graph. That's nothing that we can add up, especially if we want to analyze the banking network and its resilience to financial and economic shocks or political shocks. And we also can model that from the other way around, how many loans are going from bank B to A. And this is an example where we have an interbank network represented as directed multi-edged weighted graphs. So everything thrown in, and everything is able to analyze, and we will look into that later on in the videos.